rolling down a hill without slipping. And let's say that we want to find the force of static friction, the center of mass, acceleration, the speed of the center of mass at the bottom of the hill using both Newtonian methods and energy methods. So I'm going to start out with Newton's second law of translation. The weight of the disk as a component directed down the hill. That's mg sine of this angle here, which I'm going to call beta. There's a force of static friction acting up the hill. And I know it's static because it's rolling without slipping. Next, I'm going to take a look at the summation of the torques about point P. So we have mg exerting a torque about point P. The lever arm would be the perpendicular distance between the line of action of mg force and the axis of rotation at P. And that lever arm turns out to be equal to the radius of the circle, r, times the sine of the angle here, which is beta. So we have r sine beta, and that's equal to IP, which would be mr squared plus mr squared. I use the parallel axis theorem there. And alpha would be the acceleration of the center of mass over r. Okay, simplifying this, okay, gives us g sine beta equals 3/2 ACM, or ACM is equal to 2/3 g sine beta. So that's the acceleration of the disk's center mass, ACM. Now let's find the force of static friction. So I'm going to take this equation and substitute it into there. So we have Fs is equal to mg sine beta minus 2/3 mg sine beta. So that's equal to 1/3 mg sine beta is the force of static friction. Next, let's find the speed of the disk's center of mass at the bottom of the hill. To do that, I'm going to use kinematics with the expression we got for acceleration using Newtonian physics right here. So VF/cm should be equal to the square root of 2 times 2/3 g sine beta multiplied by the distance down the hill. Okay, and the distance down the hill we can find if we know the height of the hill, h, since the sine of beta is equal to h over the distance down the hill, then the distance down the hill should be equal to h over sine beta. So that becomes FCM then is equal to the square root of 4/3 GH. 4/3 GH. Now what I'm going to do is find the speed of the disk at the bottom of the hill using energy principles. And let's see if we get the same answer as here. Okay, so at the top of the hill, the disk has potential energy, mgh. By the time it gets to the bottom of the hill, it would have both translational and rotational kinetic energy. So its potential energy is converted over to kinetic energy of rotation and translation. So we have 1/2 m VFCM squared plus 1/2 ICM, which is 1/2 mr squared, multiplied by omega F squared. So this is the rotational kinetic energy, and this is the translational kinetic energy. Now mass appears in each term, so we get GH is equal to 1/2 VFCM squared plus 1/4 R squared omega F squared. Now since it rolls without slipping, we can express omega F in terms of VFCM and R. Recall that VFCM should be equal to R omega F if the disk rolls without slipping. So substituting after solving this for omega F into here, we get GH is equal to 1/2 VFCM squared plus 1/4 R squared VFCM squared over R squared. You can see the R squares cancel, so we get GH is equal to 2/4 plus 1/4 or 3/4 VFCM squared. Solving for VFCM, we get square root of 4/3 GH, in agreement with what we got using Newtonian physics and kinematics.